So it's a great pleasure to have Pritam Ranjan from IIM Indore. Pritam happens to be a dear friend of mine as well from Indian Statistical Institute. Pritam is an associate professor in the OM and QT area at IIM Indore. Before joining IIM, he was a faculty member in the Department of Mathematics and Statistics at Acadia University, Nova Scotia, Canada. He obtained BStat and MStat degrees from the Indian Statistical Institute, Kolkata, and a PhD degree in statistics from Simon Fraser University, BC, Canada. His research areas include design and analysis of computer experiments, statistical models for computer simulators, sequential designs for feature estimation, and a projective geometric approach for multi-stage fractional factorial designs with randomization restrictions. Pritam will be presenting the statistical modeling for dynamic computer simulators. I welcome him.
Thanks a lot for inviting me here. So the previous time I've been here once before. That was just for an informal chat with Arnabda. So I'm here now to giving a talk. So this talk is, I guess, so a very new topic for many of you. So this area is sort of new in India. I don't know why it has not been catching up in India in statistics or in some of the IS area or computer science area, but it's really a hot topic. It has been a hot topic for the last 20 years, roughly, in North America and UK and so on. So this is more or less in a general context. I'll talk about computer experiments. Okay, so first I will give you a brief about what is computer experiment, or what are computer experiments, what is it all about, and then maybe briefly, very briefly, I will talk about a recent paper that we have submitted. Yeah, and that's about this dynamic computer simulators. Okay. So what is a computer experiment? So the idea is this. I mean, you have all heard about agricultural experiments and the classical design of experiment context, but in that sense, it was the physical experiment that was done in the field in reality. Okay. But this framework is under the assumption that suppose if the physical experiment is not doable or it's really expensive to do a physical experiment. Okay. If it's really expensive, then what can you do? Either you give up on the information that you could learn, or maybe you could build some surrogate, some approximation of the physical phenomena. It doesn't have to be the physical experiment. It could be an industrial experiment, or it could be some pharmaceutical experiment, something like that. So you can approximate that using some sort of mathematical models. Okay. So think of some PDEs or some other mathematical models that you can use to model the physical phenomena, underlying physical phenomena. Now these mathematical models are of course not, good mathematical models that are complex, trying to capture the physical phenomena. They are not going to be solvable on pen and paper. So you have to approximate that and solve it, write a program and some software in some language, and so a mathematical model implemented on computers, okay, using some language. That's what we call it as a computer model. Okay, so computer model is nothing but a mathematical model implemented on computers. So this, what we are calling a computer code or computer model, is that thing. Okay, the real life experiment approximation. Okay. Now the underlying idea was that if you want to observe certain feature of the process, let's say optimization or process optimization, or identifying some key features of the underlying phenomena, if we want to do some experiment with the real data, we don't have real data, so we have this computer model data, and maybe we can do some experiments with that. Okay. So that's what we call computer experiments. So experimentation with the computer model, which is trying to mimic the reality. That's what this idea of computer experiment is. Few examples. Let's say if you want to learn about the impacts of a car crash. Okay. So what will happen if there is a crash on a head-on collision of a car to the passenger sitting in the front row or in the back row? What will happen if there was a sideway impact, and so on and so forth? If you want to know about this process, you cannot really collect a whole lot of real data. because that would mean, just going to a showroom and asking for several cars and just crashing it from all possible different angles. That's a lot of money. And so what people do have some data on it, actual real testing, as well as you can collect data from the real life accidents. So from there also you have some data, and most of the data that come from is this computer simulations. Okay, so they have built a car model, okay, and then trying to impact some forces from different sides, from different angles, from different sides, and see what are the possible consequences. So that's one computer model and data on that, and you can see some experimentation with this. Of course, some data is definitely not the physical one. There is no chance of collecting data. In this one, there was some chance of collecting some data, but in this case, if you want to know the impact of a nuclear explosion or see what would the impact force and different kinds of physics that goes in, and the environmental damage and so on in the nuclear explosion, there is no way of collecting real data. So you will have to rely on the computer model. So this one application I was particularly involved in. So this is coming from the agricultural industry. So Acadia University, what Karthik talked about, this is in a sort of a region called Annapolis Valley. Okay, so Annapolis Valley is very popular for apple and peaches and plums and so on. So there is a big apple industry in that valley, and the farmers, they were interested in knowing about a particular guy. These black dots here, these are called mites. Okay? These are called a particular kind. It's called European red mites, and they infest on apple leaves and then they damage the crop. Okay? So these farmers were interested in knowing what is the population growth cycle or the population growth pattern of these European red mites are. Now imagine collecting data on this. Okay, so somebody, or not somebody, but many people will have to go to the orchard, and actually take a magnifying glass and go from leaf to leaf on several trees and count these mites over a period of time to collect data on this. Okay? And so this is expensive data to collect. For several seasons and several years it will have to be collected to identify the growth pattern. So what some people did, they wrote down some models, computer models, to mimic the population growth at different stages of juvenile or adult or larva and egg, and to identify the population growth of these red mites. So this is data for that European red mite. This black solid curve is the actual collected data on the number of juveniles, and these other colored dashed lines are the computer model data. Okay. Some realizations. I will talk about this in a little bit more details later. Oops. Another example. So again, coming from the same neighborhood, Acadia University is here. So this is Nova Scotia, okay. And this piece is called Prince Edward Island. And if you have heard of Newfoundland, that's here, outside the map. Okay. So this is Atlantic Ocean, and this region is called Bay of Fundy. Okay. And this passage is called Minas Passage. Okay. This tiny bit here, Minas Passage. This is called Minas Basin, and this is called Minas Passage here, and this is Bay of Fundy. So billions of gallons of water come in and goes out twice a day in this, from this Bay of Fundy. Okay. Because of this big volume of water coming in and going out of here, is a huge water current. The water has a lot of force, kinetic energy, and people want to extract that kinetic energy into tidal energy, okay, to build electricity, to generate electricity. So there are some pictures here. So this is the Hopewell rocks, where you can see some idea of the people and then the water height that goes in here. Again, here you can see the difference between the water height. This happens twice a day. So there are places where a difference between the high tide and the low tide is actually 17 meters. You can imagine the volume of water that comes in and goes down, 17 meters. So people try to extract this energy. And how do they do that? So they thought that maybe, let's suppose if you build a dam here, or a barrage, what will happen? So they have thought about it, but if you build a dam here, then suddenly some part of the this region called Digby Neck region would probably drown. Some part of Maine would drown, and so that's not environmentally possible. Okay, building a dam there. So they discarded that idea, and that idea sort of floated several years ago, several decades ago. Now they are trying to put turbines, okay, like the solar, like the wind turbines. They have tidal turbines, and they are trying to put turbines into this region. Okay, so this is the Minas Passage, zoomed in region of that, and the Bay of Fundy, Minas Channel. They are trying to put turbines here. The question is, where should you put turbines? And how many turbines should you put? Okay. So this is an interesting sort of a design question. Also, there are several business questions also. From an investor point of view, they would like to know, if I am funding building these turbines. So these turbines that you see here, this is one protocol turbine, a small scale turbine, and building a turbine like this and installing, the total cost is roughly $10 million, okay, for one turbine. Okay, so some investor has to come forward and fund this entire operation of building the turbines and placing it, and then actually extracting the electricity. So they would like to know in how many years I'll get my money back out of this project. Is it worth investing? Or whether this entire project will fail and they will lose their money. What will happen? Okay. So there are a lot of interesting questions to be answered here. My part of project, of course, collecting data is difficult here, okay? Because the data that you have to think about collecting is, let's think about where should we put turbines, if we ask this question, okay? Then, so you take a turbine and put it, whether should we put here or here or here or here, which one gives me most power? How do you answer this question? There has to be a power surface, power function, and the location of the turbine is some sort of x, and you pass that as an input and gives you the power, and you try to maximize it. So from the very rudimentary level, it's a maximization problem, power maximization problem. But you can't really have the luxury of trying out different locations for the actual turbine. Okay? So you don't have the real data. The only thing that you can work with is the computer model, a model that simulates the power. Okay? So that's the computer model that we are working with, and I am involved in this project still with some toy simulator, because the actual simulator that is really expensive to run. It takes days to give me one output. Okay. So this is that Minas Passage, and we are thinking about putting turbines here. This is the denseness of the grid as well as the current speed. So roughly you get some idea of what this computer experiment is trying to do. Several interesting questions that people have in this area is, for example, process optimization. If you want to optimize a function meaning a computer model, and you're trying to maximize its output value. Then variable screening, like other design of experiments, if you are running if the objective of your experiment is to identify which factor is the most important, okay, or which are the factors that could play an important role. Say, for example, in an industrial setting, if you find out that your particular screw is defective, how do you find out that which factor is causing this defective screw? So there are 10 possible factors that are involved in the machinery, or whether it's the human force, or what factor is causing the screw to be defective. In order to conduct that experiment, you have to find out which factor is important. So variable screening. So like in the real world experiment, here also in computer models and computer experiment, we have to do some variable screening. Again, model calibration is one big area that people are working on, because so what is this idea about model calibration about? People build a model, a computer model. And assuming that, or trying, when they build this computer model, they were hoping that this computer model mimics the reality. But it's possible that they were a little off in terms of building the model. Okay? Their model could not capture the reality to the extent that they had thought of. Maybe they forgot about some assumption, or they made some wrong assumptions, okay, about the computer model. And so if there is a slight bias in the computer model, how do they calibrate their computer model to match the reality? Okay? So that's, there are several aspects of this. Model calibration is the bias correction as well as the calibration of the computer model. Then there is this inverse problem, which I'm particularly involved in. I've been working on this inverse problem idea, that if we have a pre-specified, so somewhat like the calibration or a special case of calibration, okay, that if we have some physical data, okay, and we want to see that what computer model input gives me that output. Okay. So that's this inverse problem. So basically find x such that f of x is my pre-specified y. And then if I want the overall understanding of the entire surface, that's the overall understanding. So there are several interesting problems. There are more problems to this. Currently, people have been working on this idea called uncertainty quantification. That's a big word in this area also. So one big problem in this computer experiment world that people assume that yes, this computer experiment or computer models are good. It's giving me some approximation of the physical world that we were not able to understand. But if we think about the realistic computer models, they are also somewhat slow. Okay? I mean, yes, the computers are there. Now we can try to understand the physical phenomena that we were not able to understand. But even with these fastest computers, I mean, these models are somewhat slow. Okay? So for example, in if you go to NCAR and try to talk to these guys that how long do these climate models take, you know, to predict one possible future scenario, and they'll say it takes 3 months to give to predict one output. I mean, then certainly there is no experimentation possible. You know, if a computer model takes 3 months to give me one run, and similarly, most of these big models, big real people who are making some difference in science, I suppose. You know, you go to Los Alamos or NCAR or you know, some of these big national laboratories. Their models take a long time to run. You know, or they are trying to understand some astrophysics, cosmological phenomena, and so on. Okay. So realistic computer models sometimes take too long. Then what will happen? If it takes too long, then I don't have the luxury of evaluating the simulator for many, many times. We have a limited run. And that brings the question of design of computer experiment. So we have to choose our response carefully. To begin with, so we will say that we don't have infinitely many data points. We have only finitely many data points. So let's say xi, yi, yi being the response, xi being the input of the computer model. Okay. And there are some assumptions. So to begin with, let's suppose a simpler case that the response is scalar. And the next assumption is a little bit interesting and somewhat different than the regular statistical framework, that we assume that this computer model is deterministic. What do I mean by this? So this is some mathematical model implemented in computer. So like a computer program that you have written. Okay? Perhaps I can assume that, you know, all of you have written some computer code at some point of time, maybe a small just to check the number is prime, or a little bit longer, 1,000 line or something. So if you have written a long computer code, if you run a code twice with the same set of inputs, if you get the same output, then it's called deterministic. Okay? So if you run the computer code multiple times with the same input settings, no matter how many times you run it, you get the same output. And it's called deterministic. Okay? And if there is some error, uncertainty error, or random number draws or something happening inside your program, and you may get different possible answer at the end, and it's called non-deterministic. Okay? So at a point, I mean, even now, there are several computer models that people assume that they are deterministic. Okay? So let's think about a decision tree or some sort of argument like this. These are different rules that you give for every split or for every choice that you make. And if your initial choice is fixed or initial set of criteria is fixed, no matter how many times you run this entire decision, you get the same output at the end. Okay? And that's this deterministic process idea. We also assume that the process is stationary. I mean, by stationary, we mean weak stationary processes that vaguely speaking, very vaguely speaking, and not precisely correct, that the sort of the smoothness or the bumpiness of the process is, the fluctuation of the process is same in every window of the same width. Okay? That's the vague idea. And we also assume, let's say, that the input space or the x1, x2, and so on, that vary in a rectangular region, in a nice rectangular region. Okay? We could relax all of these conditions. I'll do that a little bit. So what kind of model we can think about? What is the idea? The idea is that we want to build a relationship between x and y, okay, like any other regression model, say. Okay? So we are saying that y is some mu plus zx, and this zx is a Gaussian process. Okay? Gaussian process is a very specific stochastic process, and essentially it turns out, so mean zero Gaussian process, the mean is this, and there are several variations of this that people have worked on. I'm just presenting you the simplest one. The most important tool here is this guy, this correlation structure. That's the most important tool that controls this entire, the magic of this process to work, basically. I'll show you. The main idea of this Gaussian process model, this complicated looking structure, or this line here, is that if I have n observations, okay, from my computer model, then if I stack all of them in a vector y, then this vector y follows a multivariate distribution, multivariate normal distribution with mean, sorry, it should be mu, mu comma sigma square times this correlation matrix R. Okay, it should be mu there. So this Gaussian process, the word Gaussian, or is also normal distribution, as you can see, has special feature that you can get closed form expressions for predictors. Okay, so this is the prediction, or y hat, if you may want to think about, if I put hats everywhere, then we have y hat, and this is a nice closed form for the predicted surface. Like in the regression model, you had y hat equal to beta naught hat plus beta 1 hat x. So kind of like that, we have a closed form predictor. We have a fitted surface here, okay, using n points. And then we have some sort of uncertainty estimate. So this given is my data, given my data. Okay. So given the data, this is the prediction for the, that's right, xi yi. Yes, xi yi is given, and this is the prediction at a new value x, untried value, unobserved x. That's right. So you have to put hats here. Mu hat and R are also containing theta, and you'll have to put hats there. Okay. Now let me show you a quick illustration of this. So there are a few packages, 3-4 packages that do these kind of fitting for computer models. So this picture shows you so 1, 2, 3, 4, 5, 6, 7. There are 7 points, and through these 7, at these 7 points, we have y values. We are assuming deterministic model, meaning at this point, I have perfect knowledge of the function. Okay. If there is a perfect knowledge of this function, so I have 0 uncertainty. Okay. And at these places, I don't have any idea about the function value, but assuming stationarity and continuity of the function, I am guessing that the value of the function may lie into this bound, in this band. Okay. So that's this GP model illustration. Okay. And so this is deterministic model. If it was non-deterministic, then there would be non-joining bands here. Okay. And this, what they try to describe this as a football shape, American football shape confidence intervals here, because you will have the maximum uncertainty or lack of information in the middle. Okay. Now, this modeling framework is slightly different than the modeling framework of a typical statistical modeling, where y is f of x plus error. Okay. But here there is no error, because this error is the observation error, and all of the statistical distribution of the modeling that we see is dependent or based on what happens to this error. Okay. Most of the time we write down the distribution or model, we say y given x, and as soon as we say given, or if we do not go into the Bayesian framework, if we look into the likelihood framework, then all of this f is fixed, okay, and the distribution is on epsilon. So whether it's a normal distribution or a gamma distribution or what, or logistic or anything, that's all on error. Now in Gaussian model framework, Gaussian process, there is no error because there is no replication error. Okay. If we replicate it, since the process is deterministic, if we replicate it, we get the same output back, and so there is no error here. Now if there is no error, then the uncertainty that we are trying to describe here is not from the error bands, but this is the lack of information that we are trying to capture. Okay. Now think about just for a few seconds, suppose we have an expensive to evaluate function, okay, mathematical function, let's suppose a nice simple function, but if I tell you that you cannot evaluate that function as many times as you want, there is a budget, fixed budget, and you want to maximize that function, how would you do it? You know, so like this function, this is a function evaluated at 7 points, but if I wanted to maximize this function, okay, with a fixed number of trials or x values, evaluations, how would you do it? I mean, perhaps you won't be able to give me the ultimate maximum. I cannot guarantee that in 15 runs, in 15 x evaluations, I will be able to get the maximum, global maximum, but maybe a good approximation of the global maximum. How would we do it? Okay. And so this is another area or sub area called sequential design.
So given a value of x.
No, so the question is that if I give you a budget that you can evaluate your function on maximum 15 values, okay, you choose what 15 x values you want to evaluate your function on, so that I get a good approximation of the global maximum. I'm not interested in the entire function, I'm just interested in the global maximum.
And that is from a particular function space.
That is from a particular function space. I just don't know what is the actual function. I can get the values of the function. Okay. And so a big portion of the computer experiment literature focuses on sequential design and trying to, so the process optimization here, that's what it's talking about. And so what people do is sort of sequentially try to learn the function near the maximum. Okay. Update the information on the maximum and keep on learning. That's how you sequentially build upon. Okay, so there are several interesting problems. Now let me relax some conditions here. Okay. The assumptions that we were talking about, I had said that the process is stationary. What if it's non-stationary process? Then how do we build the model? What about the non-deterministic process if the region is non-convex? I was giving you the rectangular region, but if the region is non-rectangular and even non-convex, then even the model fitting becomes really challenging. The one that I'll focus on here in this talk is non-scalar response. If the response is non-scalar, okay, a vector or a functional or a time series response. okay, then what will happen? Again, uncertainty quantification and so on. So let's talk about this idea. So this European red mite and apple leaf. So this is the population growth curve of the juveniles over the season, and this season is roughly 100 days long. So it starts from April, goes up to October, okay, in Nova Scotia, because all the other time there is snow on the ground. And so this is the life cycle that we are talking about. And so this is one data here, and every computer model, so this is a partial differential equation 2 delay model that we are talking about. And when we run this model, it gives me curves like this. Okay. It's trying to replicate this model for different x value. It generates curves like this, and it's trying to give me this population growth curve. Okay. So this in the core of it, we have data like x. So n is the number of runs, and d is the input dimension, and y is the time series response here, 100 days long time series. And that's so each curve is one observation, okay, one computer model observation. So L is the length of the time series, and n is the number of observation. Now, the idea, the Higdon et al., they worked on this. They proposed that, well, now I simply cannot do y equal to mu plus zx, but because y is a time series, and so they said, let's look at this matrix y and do a singular value decomposition of this. Okay. And then, so this is a U matrix, a D diagonal matrix, and V column matrix. These are all basis vector matrices, and this is the singular matrices, where K is the minimum of this length of time and the number of observation. So the idea is that this Yx, now this will be a time series of length L, a vector of length L. For every arbitrary x, this can be written as a basis combination of p such bases. So there are k here, and here p is much less than k. So only take p bases from this singular value decomposition, and then write y as that. So this is sort of the explained part, and this is the unexplained part, some remaining leftover part. So that's this error part. Now, what is this bi? Bi is this weighted ui. Okay, the weight is the singular value in D matrix. And like earlier, with this part, this remaining part, we'll call it as white noise. The Ci is the basis which we model as Gaussian process. So sort of extending the one univariate Gaussian process or scalar valued response Gaussian process to vector valued or a time series response Gaussian process. There are, so here this idea of SVD based GPA I'm talking about, there are many other ideas that how one can model a time series response data.
What is x in this particular data?
The input. So for example, in this particular example, there are several possible values. For example, the fecundity and the delays, and there are several other parameters, the growth rate and so on. Okay, those things depend. Those things tell us about the population growth curve. Okay, there are, this particular model has roughly 20 parameters. Now, so this is the model that we were talking about. Basically just the basis representation in terms of the singular value plus some error, and with some calculation, you can show that I'm just skipping that. There is no point giving out all the details. That here also you can find a closed form expression for the predictor. Okay, and these are all vector of length L, and this will also give you a vector of matrix of length L, dimension L. So this is SVD based GP. The problem becomes interesting if we have really large data set. You may say that this is sort of contradicting my own statement. At one time I was saying that the data is expensive to get, and now I am saying that the data, we have a large data set. Well, there are cases where both of them are possible simultaneously. Say, for example, satellite data is really big, or for example, if you have data sets, let's say that a big complex finite element model is run, talking about this tidal power example, okay, in the Bay of Fundy. Though it takes a long time for the model to run, when it runs it, it gives me observation on every grid. Okay? And that's a really lot of observations that I get after one run. After one run, it's not one value, I have the entire mesh of information. How do I process that? Okay? So let me go back and I'll come back to this slide. So looking at this, if I run my model once, whether it may take 2 days or 5 days to run this entire model, I'll get observation on each and every mesh corner. The y value, the velocity vector or the power value, and each corner, each node. Okay? Now that's a lot of data. All of a sudden I have 10,000 or 50,000 values. Okay? How do I model it? Okay? Do I simply do a smoothing, or do I fit a model, or I don't need to fit a model? What do I do with that? Okay, so there are some sources of data where we get a lot of observations from the computer model. How do we process it? So in this context, this particular model that we were working with, the 2-delay blowfly model, the simulator was d-dimensional, this 20-dimensional. Okay. Now, in this application, if I am only interested in understanding the overall surface, try to imagine that how many evaluations would you need, even if I tell you that it takes 1 second. 1 second to run this function, this 2-delay simple PDE, it takes 1 second to give me an output. An output meaning the entire curve, entire time series curve, 1 second. But if the input dimension is 20, how many observations would you need to understand the surface? When it's a 20-dimensional surface. So in your clock time, it's really hard to do it. So think about the grid of even 10 point per dimension. Then you are talking about 10 to the power 20, right? 10 to the power 20 second. That's a lot of clock time. And that with a really crude resolution of 10 point per dimension, right? So the function to understand the overall surface, even with a really fast simulator, is difficult. Okay? So what this framework, modeling framework of Gaussian process model, or the emulation or the statistical surrogate that we are trying to fit, what this gives us is not just the idea of slow or a really expensive simulator to some understanding of the surface, but also even with the fast, but if it's a huge surface and we cannot really explore each and every corner, so in some sense it is still slow. It's not in terms of the actual running of one observation, but it's running or the exploring the entire region. Okay, it's slow in terms of explorability. And so this sort of gives us an approximate way of understanding it. Now, another aspect that is really interesting here is that if we have a large data set, let's say thousands and tens, hundreds of thousands, with this type of model fitting structure, the idea was to simply fit this multivariate normal data. Okay? And there are a few parameters like mu and sigma square, and this R has theta in it. Okay? So if you want to estimate these parameters, one way is to simply write down the likelihood and then optimize it. Okay? Now, if you have ever seen a multivariate likelihood or a function, a density function that involves the determinant of this matrix R and also the inverse of this matrix R. Okay. Now, this matrix will be an n by n matrix. If we have a large data, let's say 1,000 or 10,000, then we are trying to compute the determinant of a 10,000 by 10,000 matrix and an inverse of a 10,000 by 10,000 matrix. Okay. So, for large data sets, this problem becomes really intractable, okay, unless you do some further simplification or assumption that, well, the data must be sparse or so on and so forth. Okay. So, one way, there are several ways again of tackling this. So, one way is this idea of local GP model. Okay. So, the idea is that if I want a prediction, let's say at this cross, then the neighborhood points must have a bigger say in what my function value should be at this point as compared to a point which is here. Okay. This point will have much less influence on the function value as compared to the neighborhood points. Okay. And so, the idea of this local GP is that let's forget about all of the other y values or the x values. Let's just build a small neighborhood around this point where I want the prediction and then fit a GP on that. Okay. So, roughly that's the idea. So, there are two approaches. One is that you simply build a nearest neighbor points or a neighbor set, nearest neighbor set using the Euclidean distance, and then fit a GP model on that. So, these blue rectangles are this so-called naive approach of just the Euclidean distance based nearest neighbor, and these red triangles are this some cleverly chosen neighborhood points. And the idea of cleverly chosen neighborhood points is that you don't simply want to look at the neighborhood points, but you want the point that gives you the maximum influence. Okay. So, you want to rank the points in terms of the influence capacity and not the distance, Euclidean distance. And that's how these red points are chosen. Okay. So, I'm skipping that, and so the original idea of this greedy or this cleverly chosen nearest neighbor approach was by Gramsci and Apley, Dan Apley, but this work was extended by one of my students for functional data or for time series data. So, for one example, there are several examples he looked at in the paper. For one example, he looked at that this was the cleverly or greedy approach, what he called, and this is the nearest neighbor approach, the Euclidean distance based. And what we are looking at is some sort of error in prediction. Okay. And so, the greedy approach sort of gave less error, and here also, so this is for this nearest or the neighborhood size was of 30 points, and this was for the 50 points. Okay. Of course, the neighborhood size, as it increases, it will give you a smaller and smaller error, but with a different cost. Okay, a cost of running the model, because the bigger the size, the longer it takes to run the model, and the increment in the efficiency or the accuracy also slowly goes down. Now, this is for the MITE application. In this case, we can see that this is simply the error that we are plotting, and this error, the standardized error, is not so bad. It's most of the data is between minus 2.5 and plus 2.5, so kind of like the noise that we are looking at. Okay. So, the model did a reasonable job of fitting the data. So, just to summarize, so real life experiments, when it's difficult, computer models sort of saves, but computer models also are sometimes expensive, and then the statistical models, or what we call surrogates, are used to do the experimentation. Okay. And GP models is one of the popular class of simulators or statistical surrogates that are used. There are some other ones, but GP model has been there for since 1989. Then for this computer experiment, GP model for computer experiment. And then this dynamic computer models, this SVD based GP was proposed recently. There has been some other papers also, but not too old. And this local GP idea is for the big data. So that's all I had to say. Thank you.
Questions? Any questions for the speaker?
So in a statistical emulator, you were saying that we determine the size of, so my question is, how do you determine the size of n? So what is the appropriate data size? Like if the data set is very big, it can't be used. So that is like
the inverse problem you're talking about?
Yeah, something like you mentioned, right? That in the statistical emulator side,
Right.
you said that sometimes the data size, if it is too large, it becomes infeasible. So you fix a data set to say size n, and then you work on the model. So how do you determine what is the appropriate size of the?
See, so in this context, if you try to fit this model, okay, the big, so so there are two aspects that I was saying, that computing the determinant of R and computing the inverse of R. In your laptop, you just randomly generate a matrix, okay, and try to compute its inverse or determinant. You'll see that, with the limited memory and the swap space and so on, maybe 500 to 600, 600 by 600 matrix, you can perhaps do it. But as soon as it gets to 1000 by 1000, then that's where you hit the bottleneck and say that, well, now I need to more RAM and more swap space, and then only you'll be able to handle it. Okay? So people can still do it, but remember this, that as soon as we talk about 1000 by 1000 or data size of size 1000, these things, when you're doing maximum likelihood or any Bayesian method as well, for finding the parameter estimates, you will need to compute such determinants and inverse thousands of times, right? Because you have to try out for different parameter values and see that for which parameter value the likelihood is maximum. So doing these things numerous times, it takes a lot of space as well as time. So the practical implementation of this is sort of the bottleneck, or sort of hindering my using the full data strength. Okay. So now the question is that what's the maximum size should we go to? Is there a rule of thumb? No. There is no rule of thumb that for any arbitrary problem where I have large data set, I should stop at 100. There is no rule like that. Okay. It depends from problem to problem, that how much you can sacrifice accuracy and how much you can afford the time. Sorry? Sensitivity and affordability analysis, I guess, that you have to do.
For the data where you make a model to generate and estimate the tidal energy, sir, kind of a model which you have explained in the beginning.
Tidal energy?
Yeah, application for, this one, sir. So there, I'm sure when you were making a model and maybe estimating it on a various surface points, there you must have had some kind of physical sensors also.
Absolutely. So this computer model was, none of the computer models are built by statisticians. Okay? They are built by the subject area experts. So this computer model, this is called FVCOM, Finite Volume Coastal Ocean Model or something, Community Ocean Model. Okay? And this was built by the oceanographers and the physicists. So they sat together and with some mathematician and computer scientist coder, and they came up with this model. Okay? So we don't have any say in that model.
I'm saying something else, sir. When you were coding it, that time you must have had some physical sensors capturing the data point, accordingly you must have modeled it.
Yeah, exactly. And so those physics models were transferred into these computer models. Yes. So we had the idea that how the ocean flows, how are the currents flowing, and what are the boundaries and so on. All these parameters and factors were put into the computer model. So there is a whole different ball game of how to accurately come up with a computer model that imitates or mimics the reality.
So how will the computer complete?
Sorry? No. I mean, this is still at the early stage. So this particular turbine was placed 2 years ago. It was installed and hoping that it would do some pilot testing. As you can see that this was the process of going to install it, but it broke down within 2 weeks because all the anticipated force was much less. The actual current was so high that it broke down in 2 weeks. And so after that, they had been, I think the second pilot installation also happened or is about to happen there, okay, where they built much stronger turbines.
So this working with Gaussian process, is it different? Is it just like working with multivariate normal, or is there something different?
No, it is. Mathematically, it's a continuous, GP is a continuous process, but practically it's just a multivariate normal. Yes.
So can you fit this? Do you make some choices of the kernel?
That's right. Yeah, so that's correct. So popular choices are, one is Gaussian kernel, then there are 3 popular kernels in computer experimental literature. So one is Matern kernel that people use. Also people use power exponential kernel. But there are some other kernels also which, let's say, compactly supported kernels, or is one sinusoidal triangular kernel that people use. But the popular ones in computer experimental literature is Matern class, power exponential, and Gaussian. So you just have to make sure that it's positive definite.
I guess it allows you to interpolate, right?
That's correct. Yes, under the deterministic assumption, it allows you to interpolate. Yes. Okay.
There are no more questions. Let us start the speaker.